How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at modern atomic structure. So our objectives will be to describe the structure of an atom in terms of its subatomic particles. So meaning what is the mass and the charge of each of these particles, the protons, the neutrons, and electrons. Determine how many of each there are and interpret isotopic notation. So let's talk about atomic masses. Atoms are really small, and you probably already knew that. Typically, mass is described in terms of grams in science, but the largest atom has a mass of roughly 4 times 10 to the negative 22 grams. So it's super tiny, and it's an obnoxious number to use. So like when we're trying to describe the mass of atoms, grams probably isn't going to be our best bet. So what's our solution? The atomic mass unit, or the AMU. So 1 AMU is going to be equal to 1.66054 times 10 to the negative 24 grams. So instead of talking about grams, most of the time we'll just be describing the mass in terms of AMU. So let's talk about what that means for protons. Well, protons' mass is roughly 1 AMU. It's 1.0073. Most of the time we'll just say a proton has a mass of 1 AMU. The charge is plus 1.602 times 10 to the negative 19 coulombs, but more often we just say it's plus 1 because we count by multiples of that. The neutrons has a pretty similar mass. It's 1.0087 AMU, and again, we probably will refer to that as just having a mass of 1. So typically we say protons and neutrons have the same mass. They don't, but it really only comes up when we get into like nuclear changes and stuff. So yeah, the charge of a neutron is 0. They're neutral. Electrons have a mass that's even tinier. Like you would need thousands of electrons to have the same mass as a proton or a neutron. So it's so small that we say it's 0. It's not actually 0. It's 5.486 times 10 to the negative 4 AMU. But it's so tiny, especially compared to protons and neutrons, that we just say it's 0. Its charge, however, is negative 1.602 times 10 to the negative 19 coulombs. So more often than not, we just call it negative 1 because protons we say are positive 1 and neutrons we just say is minus 1. Right? They have the same charge but in the opposite sign. So we run into a similar issue when we talk about the size or the atomic radii. They're so tiny, our usual units of meters doesn't make any sense to use. Right? So even the largest atom is 5 times 10 to the negative 10 meters. That's not really nice to work with. So instead, we use the angstrom, and 1 angstrom is 10 to the negative 10 meters. So now this, sometimes we use picometers instead as well. So 5 times 10 to the minus 10 meters, instead of using that as the width of an atom, we can just say it's 5 angstroms, or 500 picometers. So counting subatomic particles, how do we know how many of each there are? So right here I have an isotope of carbon, right? So the number on top, that 14, is the atomic mass. Now where does the mass of an atom come from? Well, we know that there's protons, there's neutrons, and there's electrons. Now remember, electrons are so tiny that we say their mass is 0, neutrons have a mass of 1, and protons have a mass of 1. So if we're talking about the atomic mass of 14, it's really the combination of the protons and the neutrons. That gives us our atomic mass. We ignore the electrons because they're so small, it's not going to make a difference. That number on the bottom is the atomic number. Now the atomic number is the number of protons. And it's also going to be equal to the number of electrons when there's no charge overall. So if we have a neutral atom, the protons equals the electrons. Remember, the charge of a proton is plus 1 and electrons minus 1. So if they equal each other, we end up with a charge of 0. So the charge is going to be equal to the protons minus the electrons because the electrons have a negative charge. So isotopes, atoms of the same element that have different mass, are called isotopes. They have the same number of protons because that defines what element it is. So this, the atomic number right there, determines what it is. 6 is always going to be carbon. If it's not 6, then it's not carbon. Its properties would be different. So they have the same number of protons, which means they have the same number of electrons. They have the same chemical properties. The only difference is they're going to have different masses. You can see this carbon has a mass of 14, and this carbon has a mass of 12. Well, how can we have different masses if they're the same element? All right? It's because they have a different number of neutrons. So the neutrons are going to change its mass. It's not going to change its chemical properties. It's just going to make it a little heavier. So, I'm going back. So let's figure it out. How many protons, how many neutrons, and how many electrons do these two carbons have? Well, remember the protons are equal to the atomic number. So there's 6 protons in that top one. Same number for the bottom carbon. In fact, if they had different number of protons, it'd be different elements. Well, what about neutrons? Well, I know that the atomic mass equals protons plus neutrons. So if 14, I don't know why I wrote that. That's not 14. This is 14. If 14 equals 6 plus some number, well, that means that some number has to be 8. So carbon 14 has 8 neutrons. Well, what about carbon 12? Well, 12 has to equal 6 plus some number. In this case, it's 6. The number of electrons is going to be equal to the number of protons because it's neutral. They're both 6. So the only difference is the number of neutrons. All right, so how do we denote which isotope we're talking about? We're getting into isotopic or isotopic notation. It's ways of writing out which isotope we're referring to. So if I'm talking about carbon 12, you can write it out like this. Carbon 12 versus carbon 14. Sometimes they go, hey, we know carbon has an atomic number of 6. You don't have to write that. And they'll go carbon with a 12 up top versus a carbon with a 14 up top. There's also, you can just say carbon dash 12 or carbon dash 14, where the number is the mass. And that's how we're going to write which isotope we're talking about. All right, so summarize. Can you describe the subatomic structure of an atom? Can you determine how many protons, neutrons, and electrons there are for a particular isotope? And can you interpret the different isotopic notations? I hope so, or I failed you, and I'm sorry. All right, so I hope you found that helpful. I'll see you in class. Okay, bye.